Hey, how's it going there? Welcome. In this video, what we're going to be doing is we're going to begin to talk about circles. And we're going to talk about circles in a couple different ways. You can see the goals here. One is that you're going to learn to identify special lines and segments that are related to circles. And the second goal is that you're going to learn to apply properties of lines that are tangent to a circle. Okay, special lines and segments related to circles from goal 1. Properties of tangents to a circle, goal 2. By the way, you might be familiar with this word tangent in relation to right triangles. This is kind of related, but we are talking about circles here. What I'd like to begin with then, as far as goal 1 goes, is simply a vocabulary lesson. Because I did say we're going to learn about how to identify certain types of lines and segments that are related to circles. Well, that's exactly what we're getting ready to do here. You're going to see here a list of a couple of words that you're familiar with and a couple of words that you're probably not so familiar with. Radius, of course, you know what a radius is. I'll give you a definition in the picture here anyway. Same for diameter. You probably don't know what a chord is yet, or a secant. And as I said, you may have heard tangent in relation to right triangles. And there is a way to relate what we're doing here with what you've learned there, but this is really a different thing, truly. All right, let me go ahead and give you some pictures, and let's color code these things. Now, each of these things are going to be lines or segments that touch a circle or cut through a circle or stay within a circle in some way, shape, or form. All right, and of course, a radius, you know, is a line segment, and it's a line segment that connects the center of a circle with the outside edge of a circle. Alright, so that would be a radius there. And all you really need to know about a radius is that it is a segment, has one endpoint at the center of the circle, and its other endpoint is a point on the circle. All right, and then a diameter. Well, you know that a diameter is twice as long as a radius. Another way of describing a diameter is it is a segment that connects 2 points on a circle, and it goes through the center of the circle, such as this. And so that stuff is nothing new for you. And there's kind of a checklist of more of like a definition of diameter. It's a segment, goes through the center, the endpoints are on a circle. Now those things you're familiar with, we don't need to spend any more time on them, but these next three things, you, as I said earlier, might not have heard of. So let's talk about what a chord is, and I'll draw one for you first. Actually, a chord is like a diameter. In fact, I could say that a diameter is a special type of chord. Here's what a chord looks like. A chord, like a diameter, is a segment whose endpoints are 2 points on a circle. But unlike a diameter, a chord does not have to pass through the center of the circle. Now, when a chord does pass through the center of the circle, it's called a diameter. But as long as it's a segment and it connects 2 points on a circle, it's going to be called a chord. So there you go. Those are the two conditions for a segment to be called a chord. Now, then a secant is actually very related to a chord. Let me draw one of those. The thing with a secant, which you see right here, is that first of all, it's not a line segment. Well, I suppose it can be, but typically you're going to think of a secant as being a line. And the most important thing about a secant is it's going to pass all the way through a circle. It doesn't stop at one point on a circle after beginning at another point. It goes all the way through. So it can be a line or a ray, typically a line though we'll call it. And what defines a secant, as I said, is that it cuts through the circle. Now that's about all the different varieties of lines and rays that you can get that would go through a circle or be contained within a circle. This last one that we're going to talk about is something that it does intersect the circle, but it doesn't go on the interior of the circle whatsoever. And that is a tangent line. Okay? So a tangent line, it turns out, and it can be a line or a segment or a ray, it doesn't really matter, But a tangent is going to be a line or a radius segment that intersects a circle at exactly one point, such as this. So you can see there's a point right here called the point of tangency. And that is the only point that a tangent has in common with a circle. So there are the facts that you need to know about a tangent. Alright, now I'm teaching you all this vocabulary, but most of what we're going to be focusing on within this video is going to be that last type of line in regards to a circle, and that's going to be tangents. There are certain properties that exist between tangent lines and circles, and so that's what we're going to be investigating a little bit. So let's move on from the vocabulary. Well, we're mostly moving on from vocabulary, a bit more it turns out. But only a small amount of vocabulary, and really it's related to tangents. Here's the next thing I'd like to discuss before we really talk about the properties that I'm mentioning with tangents. There are certain ways that two circles can intersect one another, and then based on the ways that two circles intersect one another, there are certain things that you can do with tangents. Alright? Now I'd like to show you a few different situations in which circles can intersect one another. And one of those ways that circles can intersect is that they could not intersect, so to speak. Okay? When I'm talking about the ways circles intersect, I'm talking about how many points of intersections can they have, and so forth. Okay? So one way is that you can describe them is that they would have 0 points of intersection, such as these two right here. And if two circles happen to have 0 points of intersection and each is on the exterior of the other, they're each outside the other, then you can have what are called common tangents. Okay? And this is where the new vocabulary comes into play. I can have a line right here that is tangent to both of those circles. And so anytime a line is tangent to two circles, it is called a common tangent. And in this situation where the two circles don't intersect the way that you see, there's actually 4 common tangent lines that I could draw. Alright? Now, you can imagine the next one that I'm going to draw that's going to be outside of the two circles would be right there. This would touch both circles, right? So that would be another common tangent. And that's kind of like forming a bicycle chain, if you will. If you consider this to be a wheel and this to be a wheel, these two common tangents right here kind of form the chain, so to speak. Okay? Now, there's also a couple of tangents that could go between the two circles, like this. There's a common tangent, and there's another common tangent. Okay, so that's if two circles don't intersect one another, you can make 4 common tangents between them, which is kind of a cool thing. Now, it turns out that picture that I just showed you is not the only way that two circles could have no points of intersection. Another thing that could happen is that you could have one circle inside of another. And in that case, they don't share any common tangents because there's no way that I could pass a line that touches this circle one time that would only touch this circle one time. If it would have to be a secant line to one of the circles to the exterior circle if it was a tangent line to the interior circle. Alright, but this is worth noting right here. Anytime you have one circle inside of another and they share the same center point, the way that I've drawn it right here, what you've got are something called concentric circles. Okay, so those are concentric circles, which just means they have the same center, center with the same center. Okay, how about circles that actually do intersect one another? Well, I've shown you a couple different ways in which circles could have no points of intersection. How about when the two circles have 1 point of intersection? Such as this. Now, when that happens, we actually say that the circles are tangent or touching one another in exactly one spot. And you can see that that spot would be about right there. And I've been talking about common tangents and so forth. If the circles are tangent to one another, you can make 3 common tangents. For instance, you can make the 2 common external tangents, like what we talked about earlier. Like that and that. But you can only have one line that's tangent to both of them going between the circles, and that would have to be a line that just goes through the point of tangency for the 2 circles, kind of like that. Okay, So that's an example of circles that have exactly 1 point of tangency, 1 point of intersection. You already saw circles have no points of intersection. Here's the only other possibility that you can get, at least without the circles being the same circle. You could also have it where the two circles have 2 points of intersection. And anytime the circles have 2 points of intersection, there's only 2 ways you can draw a common tangent, and they would both be what are called common external tangents, meaning they don't go between the circles. They go on the exterior of both circles. All right, so those would be the only 2 common tangents that you can make there. Now, I've talked all I can about what a tangent is and different ways that circles can intersect and so forth. Now let's talk about some specific properties that a tangent would have with a circle. And there are 2 such properties that we're going to refer to. And the first one is a property that applies whenever you have a radius and a tangent that intersect one another at the endpoint of the radius. Okay, now you can visualize this. It's not that difficult to see. Anytime a tangent line intersects a radius at its endpoint, what happens is that segment or that tangent is always going to be perpendicular to that radius. Okay, very simple. Now you'll often see problems then where you'll have a tangent line that's connected to either a radius or to a diameter if you wanted to extend that, and then you can make right triangles out of it, such as by drawing this secant possibly. That makes a right triangle. Or if I draw say a radius, well, not really a radius, but half a secant right there, it makes another right triangle. Lots of good right triangle problems you can make with this property. But anyway, to summarize it if the tangent intersects the radius at the endpoint of the radius, then it's going to be perpendicular. Or anytime you have a segment that is perpendicular to a radius at the endpoint of the radius, that has to be a tangent line right there. Okay? Now let's work a problem based off of that. Here you see a situation where we've got segment TE that's tangent to circle C. This is the first time I've shown you this little symbol right there. You know how there's a little symbol right here for triangles. If you want to refer to a triangle ABC, you just use that little triangle symbol. Well, if you want to refer to a circle, you can just draw a little circle with a dot in front of it, or in the center of it, and that means circle. And then you put the name of the point in the center of the circle, and that's how you name the circle. Circle C tells you it's a circle whose center is point C. All right, so we've got that tangent there, and we're going to use that to find the value of x. And because we know that segment TE is tangent to the circle, and that this is a radius right here, we know that this is going to be a right triangle right there. And so whenever you have right triangles, Pythagorean theorem often comes into play, and that's going to be the case here as well. Now, I've done a little bit to trick you here, but I hope I haven't done too much. You could see where, with Pythagorean theorem, I could say that ET squared, or TE squared, whichever way you want to go with that, plus TC squared is equal to EC squared. Hope you can see, since the right angle would be there between the tangent and the radius, that this would be the hypotenuse of that right triangle. Okay? Now, I could also very easily make expressions for the length of ET, that's just x, and the length of TC, that's just the radius 8. But it seems like it would be difficult to make an expression for the length of EC, because I've only told you how far it is from E to the circle, not how far it is from E to the center of the circle. But can you use a property of a circle to kind of figure out how long this entire hypotenuse is right there? How about the fact that this segment from C to here is a radius, isn't it? That has to be 8 as well, which then tells me that this whole distance EC is 17. So there's your hypotenuse there. It's fun to use little problems right there where you have a radius drawn in one direction and a radius drawn in another direction, and you have to make sure that you use the same distance all the time for that radius. Alright, so we got x squared plus 8 squared is equal to 17 squared. And you can do the math there. I'm hoping you recognize this as a Pythagorean triple. You're going to end up finding out that x is equal to 15. Okay, so that's just one way to use the fact that a tangent is always going to be perpendicular to a radius if they intersect one another at the end of the radius. One more property that I want to discuss, and a pretty simple property at that. And that property has to do with whenever you have two different segments that are tangent to the same circle and they intersect one another at a point that's outside of the circle. Alright? And it turns out that anytime you have two tangents to a circle that intersect at the same point outside the circle, those two tangents have to be congruent to one another. Alright, quite simply, segment QR is congruent to segment TR here. Okay, now you can imagine how we might prove that. I'm not going to go through the entire proof, but I'll just kind of reason it out with you. If we use that property that we just talked about where a tangent is perpendicular to a radius, and we do that in two different places here, and then we connect this triangle, you could make a case that these two right triangles, well, you wouldn't be able to make a case, it would just be a true statement, that these two triangles are congruent to one another by HL, and so then this tangent and this tangent are corresponding parts of congruent triangles, right? All right, but very easy to realize that those two tangents have to be congruent to one another if they share an external point, if they intersect outside of the circle. So let's see one problem where we're going to utilize that fact. All right, here, same basic picture. But I'm telling you that points Q and T are points of tangency. All right, so there's a point of tangency, there's a point of tangency. And what we're going to do is we're going to find the value of x. Now, rather than draw those right triangles that I did a moment ago, we're just going to use the fact that, hey, those are two tangents, they intersect outside the circle, they've got to be congruent to one another. And we're going to use that fact to say then that x squared minus 18, the length of QR, has to be equal to 5x minus 12, the length of TR. Now, this is way too simple of a property for me not to give you a more fun algebra problem. And that's what I've done right here. We're going to have to solve a quadratic equation in order to find the value or values of x that would make that true, it turns out. Now, remember when you're solving quadratic equations, the strategy that you're going to use most often is you're either going to factor or you're going to use quadratic formula, but for either one of those, you set the equation equal to 0 first. And so what I'm going to do is I'm going to leave the x squared over here on the left side of the equation. Actually, I'm going to bring every term to the left side of the equation. Let me write them in order for x squared, then x, and all that kind of stuff. Let's subtract 5x from both sides, so we'll have an x squared minus 5x. And then we have a minus 18 over here, but we're going to add 12 to both sides, so that'll become minus 6. Negative 18 plus 12 is negative 6, right? So we'll get x squared minus 5x minus 6 is equal to 0. Now perhaps you recall that when you're factoring trinomials such as this, you want to find the factors of the constant term that add up to be the linear coefficient, and the factors of negative 6 that add up to negative 5 are negative 6 and positive 1, right? Okay, and then once you've got the equation in factored form and the product is 0 like this, you just set each individual factor equal to 0. So x minus 6 equals 0, x plus 1 equals 0, and you got two different values of x, positive 6, negative 1. Alright, great. Now both of those values of x will make x squared minus 18 equal to 5x minus 12. Although, I hope you're already thinking, we can't use one of those values. It would be impossible for x to be negative 1 here. Because if x was equal to negative 1, no, never mind. If x was equal to negative 1, you would have a negative 17 length segment here and right there. And the segments can't be negative 17 units. Now we can let it be 6 because you can have this be 18 units long, 36 minus 18, right? Or 30 minus 12 is also 18. So we are going to use 6, but we're not going to use the -1. That's extraneous. That's our solution. Okay. So in this video, you've learned some vocabulary about lines and segments that have to do with circles. You learned the relationships between two circles, how they can intersect one another once or twice or no times. And you've also learned a couple of properties relating to tangents of circles. Hope you've learned it well. Pretty simple to use. See you next time, guys.